Hello class. So on this video, we'll actually cover something that is talked a little bit about in section 2.5. So I mentioned that most of 2.5 we're covering in the homework, this logistic growth um, model that we kind of introduced in the bacteria colony example. It's further developed in section 2.5, and I'm just putting that in the homework so you can do it yourself because you have all the tools for that. There is one thing though that I want to cover because it's a really nice technique that's going to allow us to know a lot about solutions to certain differential equations without actually having to solve them. Okay? So this topic is going to be called autonomous differential equations. Again, they're talked a little bit about in chapter 2.5. You can read over it. If you don't want to, you can just look at the examples that we have here. They're all very similar, so I think it's a section that if you just want to skip and just see what I do in the lecture, it's completely fine. But still, you see that it's a very cool way of determining information for solutions without actually solving them for them. And then we'll expand on this in the next couple of videos. So after I'm done with this topic, we're going to go back to chapter 1, section 1. We're going to talk about direction fields, which are basically going to be like a more general way of finding information of differential equations without actually solving them. But you'll see that it'll be somewhat similar to what we do in this section. Okay. So that's the introduction. Again, if you want to follow in the book, chapter 2, section 5. So first, to start defining what an autonomous differential equation is, with actually worked with them before, right? So a differential equation of the form dy dx equals f of y. That means a differential equation where you have dy dx on one side of the equality, and then the other side, all you have is an expression involving y or constants, right? No independent variables at all. Such a differential equation is called autonomous. Like I mentioned, we've seen it a lot. For example, we've seen how to find solutions to this particular family of differential equations. Remember, this is separable, right? You just divide both sides by by plus c and integrate, but notice that this is also autonomous. Why? Because, well, on the right-hand side, well, on the left-hand side, you just have dy dx, so you have to solve for dy dx first, have it alone on one side of the equality, and on the other side, all you have is the dependent variable or constants. You can't see the independent variable anywhere. Okay. Now, anything of this form works. So for example, you could have something like dy dx equals e to the y plus cosine of y. This would also be autonomous. Again, because dy dx is alone on one side, and on the other side, all you have is expressions involving y or constants. Now, easy example of something that wouldn't be autonomous is anything that has independent variables. For example, if we had an x here, so x e to the y plus cosine of y, now this is not autonomous because you can see the independent variable. So again, what we want is dy dx by itself on one side, and the other side you only have the dependent variable y or constants. So very easy to tell whether a differential equation is autonomous. Now, why is this useful for us? Why are we focusing specifically on this particular case when there's no independent variable involved? So I'm going to show you what information we can get from an autonomous differential equation without actually solving it in this next example. Okay. So I'm basically just going to work everything out, and then I'll probably do one more example afterwards, and then that should be enough. 2 examples, and you'll see how important of a tool autonomous differential equations can be in terms of understanding how the solutions behave. So first, as a note, I want to write it down explicitly that we can learn a lot of information from autonomous differential equations without actually solving them. So here's what I've been saying. I just write it so you can write it down if you're taking notes. Okay. So let's work through an example. What information can you find from the differential equation dy dx equals y minus 2 times y plus 2 times y? First of all, note that this is an autonomous differential equation. Again, you have dy dx by itself on one side, and what's on the other side is just an expression involving y or constants. So that's the first thing. Now, the first property about autonomous differential equations that is useful for us is that it's very easy to find constant solutions. That means it's very easy to find solutions y equals a constant. Okay? And I'll show you how to do it. So I'm going to write it as a note. So note 2. So it is easy to find constant solutions, right? Which means solutions of the form y equals c, right, where c is a constant. Now, anytime you find such a solution, so a solution that's constant like this, we call it an equilibrium solution. And you'll see why later. So such constant solutions of autonomous differential equations are called equilibrium solutions. Okay. Now, how do we find these constant solutions? Well, actually, the process is very easy. Remember that a solution for a differential equation is a function that when you plug it in, you get equality on both sides of the equation. Whatever's on the left is equal to whatever's on the right. Now, if we choose y to be a constant, then the left-hand side is always going to be 0, right? Because the derivative of a constant is 0, okay? So let me write that. For constant solutions, or for equilibrium solutions, oops, I'm going to use the same color. So for equilibrium solutions y equals c, dy dx is always equal to 0, right? So left-hand side is always going to be equal to 0 if we choose our solution to be a constant. What that means for us is we need to look for constants that make the right-hand side equal to 0. So to find equilibrium solutions, look for constants that make the right-hand side equal to 0. And this is the process to find equilibrium solutions. Again, the left-hand side is always equal to 0 if y is a constant. So how do we make this an equality? Well, really all we need to do is worry about the right-hand side. Look for constants that make the right-hand side equal to 0. And that's the process. That's how you find equilibrium solutions, as simple as that. So let me rewrite the differential equation here. Should I go to another page or say here? Let's go to another page. So let me rewrite the differential equation. So we have dy dx equals y minus 2 times y plus 2 times y. So as we saw in the previous slide, if we want to find equilibrium solutions, all we need to worry about are finding constants that make the right-hand side equal to 0. Okay? So when is y minus 2 times y plus 2 times y equal to 0? Well, this is an algebra problem, right? So in college algebra, you would see this where with the variable y being x or t, right? Usually y is reserved for the dependent variable. But here, the name of the variable doesn't matter. We're looking for constants that make this equate this y minus 2y plus 2 times y equal to 0. What are they? Well, college algebra. Look at each factor, and whatever makes each factor equal to 0, those are going to be the constants that make this left-hand side equal to 0, or the right-hand side of the original differential equation. So for example, y equals 2 makes the first factor 0. y equals -2 makes the second factor 0, and y equals 0 makes the third factor 0. So these are the constants that make the right-hand side of our differential equation equal to 0. So these are our equilibrium solutions. So it's as simple as that. Given an autonomous differential equation, dy dx equals f of y, how do you find the equilibrium solutions? Solve f of y equals 0. So in summary, to find equilibrium solutions, of dy dx equals f of y, solve f of y equals 0, as you would in college algebra. Now, why are equilibrium solutions important? Okay. So first, let me draw the xy plane here. Okay, so let me draw a quick sketch. Let me do it in black. Right. So I have the xy plane. This is the x-axis. This is the y-axis. Now we know we have constant solutions. Say we wanted to plot those constant solutions. Well, we know that a equation of the form y equals a constant is just a horizontal line, right? So if we wanted to plot these equilibrium solutions that we found before, we would just plot horizontal lines and those y values. So let's see, we have 1, 2, -1, -2. So if I were to plot my equilibrium solutions, they would be, now, usually you plot functions as a solid line. I'm going to be plotting the equilibrium solutions as a dotted line for a reason that I'm going to tell you in a moment. Okay. So this is the equilibrium solution y equals 2. This is the equilibrium solution y equals 0. This is the equilibrium solution y equals -2. Now, why do I plot them as horizontal, not horizontal lines, sorry. Why do I plot them as dotted lines? Well, I plot them as dotted lines because of this property that I'm not going to prove. I'm just going to give to you. So let me write it as a fact here. Equilibrium solutions serve as horizontal asymptotes. Actually, let me say facts. I'm going to give you more than one. So equilibrium solutions serve as horizontal asymptotes for all other solutions. So all other functions that are solutions. So that's the first fact. Second one, non-equilibrium solutions never cross equilibrium solutions. So if you remember in college algebra, it's possible for functions to cross horizontal asymptotes, right? The only ones that we can't cross in college algebra are the vertical ones. Right? Now, in this case, these horizontal asymptotes that I'm plotting here as equilibrium solutions, they can't be crossed by other solutions, meaning that if I have a solution to this differential equation, and let's say that solution is somewhere here, that solution can never cross y equals 2 and y equals 0. That means that it's always going to stay in this particular region of the xy plane. So this could be a solution. So y equals f of x. It's not a constant solution. It's not an equilibrium solution. Right? So non-equilibrium solutions never cross equilibrium solutions. What that means is that equilibrium solutions serve to partition the xy plane into regions where the other solutions lie. Oops, I misspelled that. So for example, this graph of y equals f of x that we plotted, we can think of it as crossing through the point 0, 1. As another example, if I had a solution that I know goes through the point, what color should I use? Let's use blue. If I have another solution that I know crosses through the point 0, negative 1, then I know that that solution has to always stay in this region, right? In the region between y equals 0 and y equals negative 2. And of course, I have other options. If I have something that crosses, for example, through 0, 3, it has to stay above y equals 2. Right? So it would be here somewhere like that. So those are the three things to note. Equilibrium solutions are horizontal solutions. They act as horizontal asymptotes, meaning that our solutions are either going to go towards them or away from them as x grows larger. I'm going to talk more about that later. That's why I haven't mentioned it a lot. But importantly for us right now, equilibrium solutions partition the xy plane into regions which other non-equilibrium solutions cannot cross, just like I drew here in this graph. Okay. So now we already have some information about these solutions, right? For example, I know that this function y equals f of x that goes through the point 0, 1 can never be equal to 2 and can never be equal to 0. It can never be greater than 2 either or less than 0. So we already have information about these solutions without actually having to solve them or solve for them. So there's actually more information we can get from this. I'm going to show you how to do that in the next video. Again, we're still going to be working with the same example.